Well, if you haven't noticed yet, my Vinyasi channel has been removed and life goes on. So here we have a new recording to post somewhere else. I believe I'll be posting it on, is it the physics web channel? Oh, where is it? No, Charles Chandler. Yeah, Charles Chandler. I think I'm using the physics channel for Joseph Newman and the Charles Chandler channel. I'm not Charles Chandler, but I don't know. I thought I'd, because he studied thunderclouds, the electrical nature of thunderclouds, and I thought it was very appropriate because somebody else on a forum somewhere thought it was very appropriate. So to make the analogy, so I'm putting Tesla stuff here because Tesla's like lightning, right? You know, whatever. So it's going to be at the, let's see if I show you what it looks like. View channel. Here you go. So this is what it looks like, and that's where I'll be posting it, but I'll be hosting it here on my Tesla Pierce Arrow 1931.info website. Now, today's video is based on the background information contained in this video. When is a battery a capacitor? When it possesses infinite resistance due to dielectric separation between its terminals of differing electronegativity. In other words, we take a capacitor design and we modify it. Instead of using the same material substance for the two plates on either side of the dielectric, we change them. We choose them of a differing electronegativity. So like a dry cell battery, you might have carbon and zinc, but you have a membrane between them, allowing for current to flow in a direction opposite to the circuit. Maybe I should draw you an example here. Let's draw you an example so you know what I'm talking about here. See, this is a kind of a difference between batteries and capacitors. Let's see. So let's see. Let's just do a battery here. So we got a battery, and we got two terminals, and let's say this one is positive. Excuse me. And this one is negative. Ooh, let's make that a little longer, negative. There we go. And then we have a membrane. Usually the membrane goes right down the middle of a dry cell battery. And it allows for the passage of ions, but not the passage of chemistry. So we might have I don't know if this might be too big. Yeah, it looks too big already. That's better. All right, we might have zinc on one side and carbon on the other. Now, if we hook up a wire, let's make it red, to the two terminals. Ooh, that's too thin. Let's make it a little more stout. There we go. We hook up a wire, go all the way around. Now let's show direction of current. Let's say the current is going this way. You know, the traditional way, right? Not the electrons, the current flow. All right, I don't know. This may not be the way it's set up. Maybe I got the zinc and the carbon backwards, but for the point of the discussion, let's just fly with this. Now, an uncanny thing happens. I need blue. There's a reverse direction of current taking place inside the battery. So if we say that electrons are traveling this way, then they're going to be traveling to the right across the membrane. Now, what if we'd redesign this battery in such a way that this is no longer a membrane? Now, let's make it, what color should we make it? La-di-da-di-da. Well, it might as well be green, I suppose. Good as anything. Outline, solid, fill, solid. Okay, so we put a dielectric in between. Well, that didn't work. Oh, whatever. And let's say it's a thin plate of mica. I make it pretty thick here, but, for the point of the discussion. So let's say this is mica. Tesla used to love to use mica. It's a very good insulator. And then we use two metallic substances on either side of differing negativity, electronegativity, that we electroplate on that mica. And then we stack them in the battery, and we connect them in, how do you connect it? In parallel or in series? In series, well, if you want to create a greater voltage. In parallel, if you want to create more amp hours. Be that as it may. So here we've got a capacitor functioning like a battery, except it won't allow current to go through. No current can pass through. So this is a pure voltage source because it cannot be depleted. And it's only useful if you divide up your circuit into subsystems in which you have a pure voltage source that cannot be drained, such as a capacitive-oriented battery, and then a current source that's your drain. And you blend the two together in a magnetic field of a coil, let's say a motor. Joseph Neumann had to have a massive copper coil because that's where the blending occurred between the voltage coming from the battery and the amperage or current coming from the rotating bar magnet on the inside of that coil. So he blended the two and he ended up synthesizing electricity. That's why it's over unity, even though we can account for all the energy sources and the loss is huge. My simulations of Joseph Neumann indicates to me, see, this is what a capacitive battery looks like. Indicates to me, let's see if we can find one. See, here's one. There's only like 5 parts or 10 parts per million efficiency when you simulate this in LT-SPICE. That means a humongous amount of efficiency is being thrown away. Just humongous. Let's just sit and watch this for a little bit. These are the various schematics of the various circuits that I ran and the tracing outputs for Joseph Neumann's motor. And it went through different stages of evolution. And even before I managed to do Joseph Neumann, I had prototypes before that, and that's all on josephneumann.info. So let's speed this up a little. It's a little bit slow. Medium speed. So I learned how to manipulate the waveforms and modify them based on changing the circuit to get what I needed based on Dr. Hastings' chapter 6 of Neumann's book, The Energy Machine of Joseph Neumann. Chapter 6, he allows Dr. Hastings to take up the whole chapter and talk about his diagnosis and analysis and measurements of the Neumann motor, a small table model. And it was on that basis that I used my criteria for developing these circuits until finally I could get the circuit to function pretty much the way Dr. Hastings described and even make improvements. Now, the improvements were based on what Newman said in his book, put a capacitor across the coil, but I also put a neon bulb in there. And eventually I was able to take out the self-shorting of the commutator, see? No more self-shorting of the commutator. I just have the commutator strictly on-off 50% duty cycle. And it improved efficiency even further because self-shorting reduces efficiency in and of itself, but at the time it was necessary. It is just a suggestion. I don't even understand. I can't remember what this refers to. If you have arcing on the commutator, then you have to put in the self-shorting of 20%, the last 20% of every duty cycle, when during the last half, when the motor is off, the battery pack is off, to prevent arcing when you re-engage the battery pack. But if you make it more efficient by choosing the right capacitor value and put it on a neon bulb in parallel, or excuse me, in series with that capacitor, so both the capacitor and the series and the neon bulb in series with each other are in parallel with the coil, the massive coil, then the efficiency goes up and you don't have to self-short anymore. At least I didn't have to do that in the simulations. So let's stop this. All right, so let's go back to here. So that covers Joseph Newman. See, I needed to use Joseph Newman as my comparison because he was blending voltage with current. He separated the two, and he did not spend his voltage. And he only spent his current, but the current was not coming from the battery. It was coming from the rotating bar magnet that he spun himself with his hand. So there was an input of mechanical energy from the outside to get it started. And then it amplified its voltage because it wasn't spending any. And it was able to justify reverse current of a small amount to top off the battery pack. All because he was synthesizing electricity just like Eric Dollard tells us to do, by combining magnetism with a varying magnetism immersed in a varying electrostatic field. And you get the synthesis of electricity. Now, people say energy in has to equal energy out. That's watts. That's measured in watts. But what I'm suggesting is we recycle the voltage. We don't spend it. See, a battery will spend its voltage to run a flashlight or an electric car, and then you got to recharge the battery or replace it, or both. But here I'm suggesting don't drain the battery. Just use it as a voltage source by turning it into a capacitor so that no current can flow inside the battery in reverse direction to what happens on the outside, the circuit outside the battery. And thus you'll have these two terminals, like Thomas Bearden says, don't kill the dipole. So you don't kill it by not allowing current to flow at the voltage source. Well, he never said to put the current somewhere else, but that's how else are you going to do it, right? You got to put the current somewhere else other than the battery. And this is what John Bedini does. He doesn't return the current back to the battery. He sends it somewhere else. So it's through trickery, you know. But you got to, well, you can say trickery, but a nicer way would be to say you divide your big problem down into smaller parts because it's, you know, so-called free energy is a very complicated thing. It's not as simple as it sounds. And so you take, you know, any good advice says you take a difficult problem and you try to see how you can break it down into its component parts. And that's what Eric Dollard says. You synthesize electricity. You're not creating electricity, you're synthesizing it, because if we analyze it, well, what are we creating? In the case that I'm suggesting here, I'm recycling volts, but I'm creating current, and I'm destroying current as well. I can create and destroy current, and if I recycle the volts, then I'm going to get this, either the synthesis or the decomposition of electricity. Now here's a Wikipedia article on current source. This is a very vital article, and I actually put some external links at the bottom, and nobody objects, so that's fine by me. Let's see, where's This, I'll let you read it. Okay, I'm not going to highlight anything. I'll let you read it. Now, so what I did was I took Sir Aman, and I thought to myself, you know what? What if he's doing what Tesla did with Pierce Arrow? He had two globes on either side of the front end of his car over the headlights, two metallic globes. And I began to think to myself, you know what? Maybe we don't understand Tesla's Pierce Arrow very well. We're told there's an aerial that he added to the back end of the car. What about the aerial that was already there to supply the radio? That means there were two aerials. If he disconnected the radio aerial, let's say, if you have to, I don't know. But let's just say for the point of discussion. Now we've got two aerials, one that was already there plus one in addition, and they're at opposite ends of the car. Well, Sir Aman did something similar, although he didn't do them on opposite ends lengthwise. He did it opposite sides widthwise, across the left side of the car versus the right. So imagine this is a car, and you got the right headlight over here, and the left headlight over here, because the car is pointing to the left here. And this is the rear end of the car, where the rear end of the car. And the transformer here is at a 0.5 coupling coefficient, which is very low, because that's about what happens in a motor. It has an extremely low coupling coefficient. That means a loss of efficiency. That means whatever happens on one side, it takes a long time to get over to the other side. You have to wait a while, a big time lag. And by the way, this is the shortcut to the circuit, and this is the shortcut to that video I just showed you on when is a battery a capacitor, or when is a capacitor a battery. I forget the title now. Maybe it was when is a capacitor a battery. Anyway, let's see, what am I getting to? So I made this 2 Henrys because 1.7 is about what my car is. It's not going to be the same for all EVs. My car is massive. It's over 3,000 pounds. In fact, it's around 3,400 pounds. The Pierce Arrow was over 4,000 pounds. So you're going to need a lot of induction, in all likelihood, in the motor running the car. So I computed, estimated, somewhere just under 2 Henrys. So I just rounded off for this simulation, made it 2 Henrys. 1-to-1 ratio. I did not change the ratios any. I could have, for improved efficiency, but to demonstrate the proof of concept, I'm keeping things simple, and I kept it 1-to-1. You can change the ratio between the primary and secondary to improve efficiency, but I don't have to do that. And you don't either, because technically it's not a vital part of this demonstration. This demonstration is demonstrating a current source. So if we already have another subsystem within the electric circuit, the electronic circuit, that supplies the voltage that will not be depleted. In other words, let's say a battery pack that's structured like a capacitor that prevents current from flowing through it internally, and thus prevents current flowing external to that battery. Now you've got yourself a capacitor, but with a permanent voltage difference between its two plates, because they are of different galvanic electronegative value. Let's say you took a thin film of mica, and on one side you put zinc and the other side copper. Duracell copper top battery, So, well, no carbon. And then you can make it very thin, and then you can stack them. See, there are two stories to Tesla's Pierce Arrow, and the minor one gets short shrift. And what I'm doing is I'm combining the two, thinking to myself, you know what? I bet he had batteries in there, but they were not batteries. They were capacitors supplying a constant voltage source that could not be drained of its voltage. And then he had to have a current source, and that was probably what was inside his project box, supplying what would be drained. Because I can synthesize current. I just can't synthesize electricity. If I take, a constant voltage. See, this does not produce voltage. You actually lose voltage in the course of producing current. But they're not really related to each other if you study this thing. And I'm doing my measurement on one aerial, okay? Because Paul Falstad doesn't allow you to take measurements of the transformer and put it out here. You can put it here, You know, you can put your cursor over the transformer and see what happens in the lower right. But due to the varying nature of the dynamic nature of this circuitry, it's kind of hard to follow. So it's nicer to see it scoped out here, traced out. Now I use a 6-volt battery to get it going, and it's a snap switch. You know, only so long as I push on it does it remain closed. So I just do it like that, and I got this huge resistor here, 100 mega ohms, so that I never use more than 60 nanoamps of juice from this battery to get this thing going. Okay? Now, I could have lowered this capacitor down as low as I want to. The lower the better. But what I'm going to be doing here is I'm going to turn on the simulation, give it a snap switch charge from the battery, and then the battery is no longer involved. So I don't scope it here. Trust me, it's 60 nanoamps of a spike, a very momentary surge that gets this thing started, and then it's not part of the picture anymore. And I'll be raising and lowering the amperage on this aerial right here. And the tendency overall is infinite gain. So that every time I lower it, on average, versus every time I raise it, on average, the overall average goes up. But it's stepwise. Now remember part of the story that we know, the one that circulated a lot, that Tesla made a few adjustments when he turned it on and he looked at his meters. I think he was ramping it up, the current. By flicking, what you do is you flick this capacitance up and down, up and down. Remember, he invented vacuum tube variable capacitors in 1896, filed for a patent, and never received it. And a year before his death in 1942, they became commercially available. Doesn't mean that he had somebody making them for him, either in his lab when he had a lab, or when he didn't have a lab, like in 1930, maybe somebody in Buffalo, New York, you know, where he went to do the demonstration, was making them on you know, maybe just for him, you know, whatever. But that's probably why he had the demonstration in Buffalo, New York, because he picked them up there. So you can vary the dielectrical property of that vacuum tube capacitor up or down. And it's unbelievable. You actually can improve efficiency of raising this thing up more rapidly towards an infinite gain. In other words, any amount of amps you want. Now, the bigger the flip of low to high and high to low, or let's say, well, I haven't done a thorough examination, so I'll just generalize and oversimplify, but it may not be entirely accurate for the purposes of this discussion. The greater the rise from a low value of capacitance to a high value of capacitance, the greater will be the jump of the current down here. Now, the output here is AC. We got it started with DC, but the output's AC, so that satisfies the criteria of the story that it was an AC motor that was put in there. And here we have an AC motor, which is part of the circuit. Okay? The AC motor is where we're going to be blending everything, the current and the voltage, ultimately. So it's part of the device. It's part of the power supply. But we need only put the capacitor on one side opposite the two aerials, with the motor in between. Now, it's not uncommon to put a capacitor across an AC motor if that motor is a single-phase motor, in which Tesla actually invented a self-starting AC single-phase motor by adding an extra pair of coils. He'd have a pair of coils opposite each other, and the thing would just wiggle back and forth due to the nature of AC current. But then, at right angles to that, he put another pair of smaller coils opposite each other, and that got it started in one direction or the other. So, let's see, what else do I need to say? There was a few other things. So if you want a big rise down here, you need a big gain. So that means you're hobbling up and down to a large degree. So earlier on when I was experimenting, I had like 1 femtofarad, and I'd go up to 1 farad. But when you're trying to fine-tune it, you don't want that big gap because you'll overshoot and have kiloamps or something, or hundreds of amps when all you want is 200 if you're accelerating in an EV, or 60 amps, let's say, if you're cruising. At least that's what happens in a DC motor. I don't know the characteristics of an AC motor, so I don't really know what you'll need. Again, for the purposes of the discussion, I just have to pick and choose numbers and carry it over from a DC electric car situation because I don't know any differently for an AC situation. But here I start out at 1 millifarad because it doesn't matter. It takes a little longer to get where you need to go, but not that much. The main problem, it seems to be, is the upper boundary works best at a minimum of 1 farad. You could go higher, but you don't have to. But you can hobble up and down at a lower level below 1 farad. It can be a lot lower or a little lower, but your upper bound, start out, try using 1 farad and see how it works, and then you find out what works best. I've just done enough experimentation to understand how to operate this thing so I can tell you. So I'm giving you in this video an operator's manual on how to develop this circuit into a current source of any value. It won't have a whole lot of voltage to speak of, but you'll take care of that with another subsystem in your electrical circuit and blend the two together in a magnetic field of a coil to get the proper volts and amps that you want. But you don't want to spend the volts. That's a big no-no because it's the easiest thing to lose and it's the hardest to gain. While amps, it's the easiest thing to get current. My God, it's so easy. And so when we say energy in equals energy out, fine and dandy, but that does not apply to current. Current in does not equal current out. And you know why? The perfect example is a negative resistor of a gas discharge tube such as a neon bulb. Classic example. Anyway, let's see what else. I think I've covered just about... Oh, no, there's one more important thing right here. Another version of Eric Dollard's LMD hidden inside of Tesla's Pierce Arrow. See, Earl Amon, it can't be this easy, can it? And this works equally as well at vinyasa.info/realsim. Right now I'm operating under the original simulator that doesn't have too much difference between mine and Paul Falstad's, just that I took away the limits on diodes and transistors, but there's no diodes and no transistors here, so we don't have to worry. So this functions pretty much the same as Paul Falstad's simulator does. But this circuit will work just as well in the so-called realistic simulator, in which I put equivalent series resistance inside of coils such as transformers and capacitors. Works just as well. It actually works a little more efficiently in the realistic simulator with equivalent series resistance inside of coils and caps. But it's not like you can't do it this way. You can still get away with doing it this way, and it'll still work pretty good. It just takes a little longer hobbling up and down to get to where you want to get to. Now I chose 6 volts DC because that's the size of the battery inside of cars, internal ICEs, internal combustion engines, oriented cars back in the 1930s. And by the way, they were not grounded negative to the chassis; they were grounded positive to the chassis. Be that as it may, I thought I'd choose 6 volts DC for this demonstration because that's what was available at that time. What else? So this capacitor here has nothing to do with the mica capacitor that I had explained before, because that had to do with a non-drainable voltage source. This has to do with a current source that we can synthesize and we can decompose. We can raise it and we can lower it. If I put in another output here, let's do that. Let's put in... so this will be strictly volts, and it'll show you what's happening up here, so you can see the difference, see what I mean, because the voltage is like really minuscule. I mean, normally it's 15 to 20 volts on these antennas, which is kind of large, but this is just proof of concept, so I'm not going to worry about that. But it goes down to something like microvolts. It's really small. And you'll see the behavior of the voltage has no relation whatsoever to the current. Absolutely none. The voltage is doing its thing. It's going more and more increasingly in the negative. And I think what it is, it's a very slow sine wave. It's so stretched out that we won't be able to see it reach its bottom out and then rise back up again and up and down and weave up and down like a sine wave does. This circuit is pretty much an AC-based circuit. Only when the battery is engaged does it try to change that. And if you were to hold the switch down for any length of time, you'd see the current going around, and once in a while it would jimmy backwards for a slight moment and then go back forwards again. And you'd be draining the battery like crazy. You know, it would explode long before, you know, because in the simulator it goes up to kiloamps and whatnot, you know, so you don't want to do that. So I put a resistor here to prevent that and a snap switch. And I'm giving you instructions. Just a snap is all you need to get this thing going. The real magic is to raise and lower this capacitor. So let's stop talking. Oh, there is one other thing I have to tell you. What's the empty space between these two aerials? It's a dielectric of air. We could have used earth ground and it would have been the earth. But that would have been not a dielectric, unless, of course, it was bedrock, without any conductivity in the topsoil to speak of. But in air, we've got a pretty good chance of this being a dielectric, especially if the two aerials are spaced far enough apart. You'll have an ionic channeling between them, so there will be some current, but a lot of resistance. And so the shorting going on between these will be vastly reduced. When you think about it, it's like we got another capacitor over here, or a resistor, depending on see, in the case of aerials, actually it's a capacitor. Right. So there's an invisible capacitance here between these two aerials, especially the way C. Earl Lamont set it up. You see, we're told in the story of Tesla's Pierce Arrow, he put the aerial on the back side of the car. Where's the radio aerial? We don't know. The whole point is you don't want airflow to go in series across them, because then it'll encourage ionic channeling, let alone arcing between them. But if the airflow is going this way, perpendicular to the arrangement of the two aerials, now you've got an improvement of capacitance between them, ensuring that they won't short out between them, not even ionically, because all the ions are being thrust backwards, at right angles to their relationship here. So this is not a resistor between them of the air. If we do it the way C. Earl Lamont did, and put one over one headlight and one over the other. And by the way, he didn't use aerials, as Tesla's Pierce Arrow story tells us. He used bronze spheres, hollow spheres. And that's perfect because it sets up capacitance, a charge inside that sphere, and a lot of surface area for the air to flow across. An aerial has very little surface area, and so it's not very efficient. So if you want to use aerials, don't use a standard aerial, because you're not trying to pick up a radio station. We're not doing what the standard story is, 12 radio tubes to tune into some source of energy exterior to the car. No, we want to dissipate. We want to create references, an electrodynamic reference to the circuit, and we want to ionize the air surrounding it, but we want it to build up a charge, and so a hollow sphere made of bronze sounds pretty good to me. See, as little as we know about C. Earl Lamont, it's enough. We can make do, because it's Eric Dollard's LMD, in which we have 2 coils and 2 capacitors. And if you know anything about my prior design work, I realized that a transformer with a capacitor on either side is equivalent to Eric Dollard's LMD analog computer, if we maintain this horizontal approach to how we deal with it. For instance, the way the battery is set up. It's set up in that longitudinal fashion in which the capacitor... Oh, no, excuse me. Oh my God, this is not LMD, this is TEM. Whoops. At least that's the way we started up. Huh. It's hard to say because we only have one module here, but the way we started up is TEM version. So we started up as TEM. But the way the aerials dissipate their charge to the passing air is LMD. Right? Because they go this way. Right. Oh God. Now I don't know. Oh shoot. Actually it's TEM. Yeah, because the flow of air is perpendicular to the capacitor. And the capacitance, I don't know. If the flow of air is perpendicular to the capacitor, it might be LMD in its operation, in its characteristic operation. Anyway, whatever. It's an analog computer of the simplest variety in which you have two capacitors and two coils. But the missing capacitor is implied or inferred from the dielectrical space of air between the aerials and the flow of air cutting through at a perpendicular. That's all we need to know. So this is the beauty of the simplicity of this thing. It's utterly simple taken to the nth degree. Unbelievable. I'm still blown away just talking about it. So let's start up the simulator. Now I have a 1 second time frame because I'm in a hurry. I don't want to wait forever. And it doesn't change anything. You know, usually when I do these circuits, if you change the time frame, it changes everything. And normally you get better results if you reduce the time frame than if you increase it. Well, this one, it doesn't matter where you put it. Just whatever's convenient for you. Now notice what happened. Already, the voltage source is accumulating a negative charge on these aerials. I'm only looking at one, but trust me, the other one is doing the same thing. And the amps is pretty much at atto amps. It's very small. Now we give it a flick. And if you look, where is it? Oh, dear, dear, dear. It's at 4 nanoamps. No, 32, the negative down here. Yeah, when I said 60, that was what it cost the battery. So it cost the battery 60 nanoamps, and what it delivers is 40. So let's do that again. So you have to look down here, and it's hard to see it. Darn it. Oh, I know how to fix that. Let's swap the battery terminals. See? 30 nanoamps right here. 30 nanoamps. And that's half of what we get over here. Or excuse me, not here, but what we get on the battery drain is 60 nanoamps. So now I'm going to take out the M. So now it's 1 farad. Now I'm going to reduce it down to femtofarad. See, already it's thickening up here. And then, oh yeah, I did that. Okay, and then I take out the femto and go back up to 1 farad. And look at that. Huge gain. Now we're up to milliamps. Now I'm going to be very careful. And since 1 farad is equivalent to 1,000 millifarads, I'm going to take out 1 0 and drop it. And actually that increased the amps. How about that? So let's increase the farads. Okay, 15 milliamps. Let's take out a 0. Now it drops. And now we add 1. So I'm just going by a factor of 10 here. So you can see it here. This is 1 farad. Now we didn't get much gain, but that's okay. You take out 1 and apply it. Now we've got... Oh, wait a minute. Ah, shoot. This is what happens when I don't wear my glasses. 1, 1. Oh, shoot. No wonder things are not happening the way I want them to. Alright, let's go back to 100. Okay. Now, that's more like it. Okay, so now we drop it down. And it doesn't go down that much. See how little it went down right here? So now we add another 0. And we don't get much of a gain. That's okay. Now we reduce it. Big loss. Add another 0 back. We're not getting what I said I claimed I would get, huh? So maybe I'm not doing enough of a change. Alright, let's go a little further this time. Let's go down to micro, see what that does. Oh, interesting. And then go back to farad. Ooh, there we go. 3 amps. Now we want to micro tune this, so let's go to 1/10 of that. And that drops it. And then let's go back. See. Now we've got 5 amps. And it drops it ever so slightly. But now it goes up to 14 amps, it looks like. Okay, now we go over to there. So I'm just doing a little bit at a time here. See, that didn't drop hardly at all there. But it shoots up to 40 amps. Now, cruising speed for a DC motor is 60. So we'll do one more change. We want to accelerate comparable to what a DC motor would need. So I'm looking for 200. That didn't do much. Alright. This is going to be too much. There. So now I've overshot. 335 amps. And look at the volts. It's still doing its thing all this time with no regard to what I'm doing. Now, because this is 1 farad, it's not going to lose its amperage anytime soon. It's stored so much energy there that it's just going to keep going and going and going like the Energizer Bunny. So we've pretty much got a constant current source going on here. And if you read the Wikipedia article, they say, in theory, if you were to have a current source or a constant current source, regardless of voltage, because look at this, regardless, you've literally got infinite energy capability, what we like to think of as free energy. So they're giving us, and this is, see, now people say this is not realistic because this is just a simulator. I'm going to be nice about this and not derogatory or expletive. There are 2 realities, and we fail to see the difference between them. There's the world of the abstract and the world of the concrete, and they're both real. Plato calls the abstract world the ideal. And that's right, this is ideal. In the concrete world, it's anything but ideal. But that doesn't make the abstract any less real. It's just not concrete. So this is an indication of what to look forward to, but that doesn't mean this is how you do it. It's something to keep in mind, though, when you try to go and replicate this in the real world. But that doesn't mean it's going to work this way. Because it's teaching you a theoretical principle, an abstraction, that works perfectly in the ideal world of the abstract, but may be problematic in the concrete world when it comes time to build it. Yet it's utterly simple. So either this is totally screwy or totally on the mark. You can't, it doesn't get any more complicated than this. This is so simple, it's unbelievable. And I can keep doing this and build up the current to any value I want to. And it's nothing new. I've done things like this before. But if I go and put this in the realistic simulator, I get the same results. It works just as well. So you see there's no resistors here. I only have one here to make sure I protect the battery from being overly drained. So that means that this response here is pretty favorable. But if I have an equivalent series resistance of a coil built in and of a capacitor, it still works pretty good. So this is a current source, and we have to blend this with a voltage. And this is what's going to be drained. And the voltage we don't drain. We recycle it. We just use it as a constant source of pressure, but we never drain our voltage source. It's a big mistake, and that's basically what Thomas Bearden was saying, is don't kill the dipole, is he was saying don't drain the voltage source. And then we blend the two in a magnetic field of an electromagnet, such as the coils of a motor, an AC motor, and then we get exactly the volts we want and the amps we want, or in the right ballpark. Now, in Tesla's demonstration, it was purely analog. It's not digital, so he wasn't looking for exact results. And so when he was working the throttle, the foot pedal, the accelerator pedal, he was doing it by touch, and he was trying to get a feel, I would imagine, for how to operate that pedal to get these results. Because you notice I have to lower in order to raise. And so if he's pumping the foot pedal, in order to raise the current that he's supplying to the motor, that's getting its constant voltage from a capacitor-style battery bank under the hood that he didn't bring with him. All he put on the project box by him might have been the current source. Then it might have taken a little bit to get a feel for it. Once he got a feel for it, he could explain, with ease and comfort and assurance to his associate how to run the thing so that he could relax and talk and not think about driving. It's not that hard once you get the hang of it, I'm sure. It's just a new skill like anything else, just like a driving skill. But it's a little different than what we're accustomed to, and I suspect it's possible that's how you approach this. Raising and lowering the capacitance here, you have to take a step back before you go forward. You have to reduce the capacitance before you raise it again. Now, you could just keep raising it. See, you could do that too. You could start with 1 femtofarad in the beginning and just keep raising it. And you'll get to the value of current that you want to reach, but that's kind of ungodly, I mean, who wants to do that? And it's not even possible. That's not buildable. But all you have to do is go up and down, and you'll achieve the same effect as if you were to be raising the capacitance ad infinitum, with no limit imaginable. So these are workaround little tricks, and he invented the darn thing, the variable vacuum tube capacitor, so that he could do that. He could toy with the capacitance and play with it and make it go up and down while it was running. And if you try to do this in LT Spice or Microcap, forget it, because it's not a dynamic simulator. Only in Paul Falstad's simulator can you do this. Maybe somebody else has come out since, Paul was the first, if somebody else has, to come out with the idea, to do a simulator that's an ongoing dynamic relationship between the user and the simulator, so that I can flick switches and change values on resistors, which, normally use a potentiometer for that, but we don't do that. We do it on the capacitor. So I think I've covered everything, and I'm going to shut up and let you digest what you've seen, because it's truly a phenomenal idea. Now, I don't know how Cyril Amon did his thing, but I did take information from his electric car version. He had a version that ran his house such that he disconnected his house from the power grid, and then he had another version for his car, and it's those 2 brass globes over the headlights that told me what I needed to know about the quantity of aerials. I needed to double them. I had to make them 2. And I had to do it the way he does, with the airflow going between them, to make sure that only capacitance and no resistance occurs between them. And then it works like a charm. It's truly a remarkable concept in its utter simplicity. This is just a concept, okay? Like concept cars, they only make one. Well, this is a concept simulation. So we get the concept in our, burned into our brain, the utter simplicity of it all. And then the building of it, it will be another story entirely, filled with complications, I can imagine, just, off the cuff without even dreaming up what those complications might be. So don't take this literally, and don't think that it has anything to do with the concrete world that we live in. It has to do with the abstract world of the engineer. Because when you sit down to engineer to build a bridge or compose a symphony, it's all abstract, It's not concrete. When you go and play it, that's concrete. Or when you build the device, that's concrete. So let's keep real out of it. I use real because, I wanted to put more realism into Paul Falstad's simulator. But that's not to say that simulations are not real. They're just not concrete. They're abstractions based on abstract formulas that are busy computing all this and then spitting out the results. But look at this. The voltage has absolutely no relation to the amperage whatsoever. The amperage is going up and down and rising overall, but the voltage is doing its own thing, slowly rising in the negative direction. And trust me, this yellow band here is a very tightly packed wash of color indicating an AC sine wave, because I've played with this already at different values, and I can change and get a nice up and down sine wave. It just happens to be squashed at the moment. Now I tried to indicate, it says it right here. Look at that. See? 40 hertz. If I put my cursor over it, and you look right there, 40 hertz. Now I asked it to show me the frequency. See? I have it checked off along with the RMS, but it doesn't want to tell me here. But it will tell me over here, if I put my cursor over it. It won't tell me the... Oh, no, it does tell me the RMS. Let me look with my glasses. You can see it, but I can't see it. RMS is 3.5 volts. But it doesn't tell me what the RMA is, or ARMS, the amps RMS. It tells me 400 watts on average, but that may not be RMS. Yeah, so the voltage is only 3.5 volts RMS. The maximum is 5 volts. Is it really? Let's see. No, that can't be. Can it? No, because it's right here. Oh, it's probably varying to 5, negative 5 actually. In here, that is. The other one I think is flipped, possibly. Yeah, it's reverse polarity. Oh, let's see about that. Well, let's see. No, they're both negative. It's not reverse polarity. Anyway, so these are sine waves. You just don't get to see them because they're so tightly packed, but they are there. Anyway, so this, hey, we're zooming in. We're gonna figure out this thing of Tesla, and Sigur Rós has something to contribute. Okay, now I can shut up.